will continue our discussion on protein denaturation. So, in last class we looked at thermal denaturation effectively. So, what we saw was that there were a couple of ways of doing that. One was we started with a two state model, right, and using that two state model we derived an equation, and we said that any thermal transition based on any spectroscopic or any observable y can be fit to that, can be fit nonlinearly to a least square fitting of a certain equation, and you can get the corresponding thermodynamic parameters. Then we said that the other way of doing it is taking delta H from the Van 't Hoff equation, and the best way of getting delta Cp was, what was it? That means you subject your protein to different pHs, right. So, pH will change Tm, and from the plot of delta H versus Tm you get what? Delta Cp, and that is the best way of getting delta Cp. So, today we will shift gears a little bit and we will go to chemical denaturation. So, chemical denaturation, as you can see on this slide, essentially chemical denaturation is brought about by two main compounds very popularly or very commonly used, very popular, very commonly used. One is urea and one is guanidine hydrochloride, right. Now, as it says on the slide, guanidine hydrochloride is a stronger denaturant than urea, okay, and it is proven. Also, there is one major difference in between these two. What is that? Urea is a neutral molecule, right, but what about guanidine hydrochloride? It is actually a salt. So, guanidine hydrochloride might also have a huge role in electrostatic interactions, because it itself is a salt, right. It can act like a salt along with the fact that it is a chemical denaturant. So, does this bring about any difference other than simply the fact that guanidine hydrochloride is a stronger denaturant than urea? Maybe this is one of the reasons, we do not yet know. But let us go forward and look what chemical denaturation is all about and how is it different than thermal denaturation. So, the starting point is very similar, right. The starting point is, again you take a two state, that means you are going from N to D, nothing in between. So, delta G is given by this equilibrium constant, and then you have this, we have derived this yesterday in class, okay. And here y of t is given by this expression, but remember when you are doing a chemical denaturation you are varying what? You are varying the concentration of the denaturant. In thermal denaturation you are varying the temperature, right, everything else remaining fixed. In chemical denaturation you are keeping temperature constant, but you are varying the concentration of the denaturation. That is why it is also referred to as isothermal denaturation, because you are doing it at the same temperature, okay. So, then I can refer this one, say I can refer well this one as isothermal denaturation, okay. It is done at a specific temperature. Now, how do we model a chemical denaturation? The best way to do it is by something known as linear extrapolation method, in short form LEM. Now, this is very commonly used. What does it refer to? It says that from many studies chemical denaturations or chemical denaturants have been found to interact with proteins in a manner that the free energy of unfolding varies linearly as a function of the denaturant. That means, if we are looking at delta G, what was the delta G? That was delta G was delta dn, remember, delta G d hyphen n. If you are looking at that free energy of unfolding, this statement says that it has a linear variation with the concentration of the denaturant, which means I can write down something like this, that delta G, which is essentially delta G dn or delta G unfolding, is equal to delta G H2O minus m concentration of denaturant. So, this is a linear variation where m is the slope, right. What is delta H2O? What do you think is delta G H2O? Yeah, under what conditions? Say delta G H2O is your intercept, right. At the intercept, what is the concentration of the denaturant? 0. So, essentially delta G is that change in free energy where your concentration of denaturant is 0. Okay, that is what delta G H2O means, right. That is why it says H2O only, because you do not have any denaturant, your denaturant concentration is 0. Okay. So, as I said, the delta G H2O is the free energy of unfolding at 0 denaturant. But do you think it is easy to get under normal conditions? What do you think? Would it be hard to get? First of all, it would be based on what? See, when you are saying this free energy of unfolding at 0 denaturant, here there is a problem. The problem is, if your denaturant concentration is 0, how would you talk about free energy of unfolding? Because your denaturant concentration is 0. If your denaturant concentration is 0, then essentially you are not unfolding the protein, right. Then obviously this question about finding delta G H2O under those conditions will not arise. Why? Because essentially there is no denaturant. Almost all of your molecules are in the folded or native state. So, how do I do that? Maybe this is where this linear extrapolation method comes in. You think about this, we will soon see it. If you would be able to calculate delta G, now remember, when we talk about thermal transition, thermodynamics is very similar, it is just the application which becomes different. When we talked about thermodynamics, or rather when we talked about thermal melting, what did we say? The one which we are interested in most is the transition region, because that is the one where the maximum change is occurring, and that is the one which is giving me the most reliable delta G value, right, because that is where I have measurable concentrations of folded and unfolded or denatured and non denatured states. Now, the same thing is going to happen here. If I get delta G in the transition region for a series of denaturant values where I have appreciable amounts of denaturant present along with the native state, and then if I am able to extrapolate it linearly to my y axis, which is essentially my delta G, then that extrapolation at 0 point, essentially where x is equal to 0, should give my delta G H2O, is not it, because it is a linear curve. So, that is what people do. You have to extrapolate it, because under the native conditions your delta G is very hard to get, and obviously if your denaturant concentration is 0, what delta G are you talking about? Okay. So, this is the basic premise, or this is the basic hypothesis on which this linear extrapolation method is based. And as we just discussed, m is the slope, it is a measure of the dependence of delta G, that is the change in free energy, on the concentration of the denaturant. Okay. So, some some papers or some books will refer to this concentration of denaturant as D, or you can also write it as C or just C. We will mostly use C. The problem is, if I use D, then I have already referred to my denatured state as D. So, we just want to avoid that complication in terms of the same symbolism, okay. But either of these can be used. Okay. The next, again we have this equation, we are going to fit, I will show you the transition will be very similar to a thermal denaturation transition, okay. But y at that specific temperature where you are doing the denaturation is y n plus y d times the k equilibrium, which is equilibrium constant, over 1 plus k. Now, what is y of n? Remember, when we are doing thermal unfolding, we had seen this baseline thing, right. So, here also we have the same thing. In that case, you had what? You had m n times T, because you are varying temperature, plus an intercept, say A of n or B of n. In this case, what are you varying? You are not varying temperature, you are varying denaturant concentration. That is why you see it is y n is equal to an intercept alpha n plus beta n, which is the corresponding slope of that native state as a function of denaturant. See, the hypothesis or the approach is very much the same. The only thing that is changing is, instead of temperature dependence, you have a concentration dependence on the denaturant. That is the only change you are doing. So, similar thing will happen for the unfolded state baseline or the denatured state baseline, which is y of d, right. And then k can be expressed like this, where obviously in that case delta G had a huge temperature dependence. Remember, delta G of T was equal to delta H 1 minus T over T m and all these things, but that was the temperature dependence. Here we do not care, we are doing it at the same temperature. So, but here we know that delta G has this linear dependence on the concentration of denaturant. So, that delta G is replaced by delta G H2O minus m times concentration of denaturant. Okay. So, if you are given a transition curve, you essentially fit this, where alpha n and alpha d are the respective signals at 0 molar denaturant, that you can understand, y n and y d, right. Beta n and beta d are the slopes of the baselines for native and denatured states respectively. Okay. The unfolding transition is induced in, the unfolding transition induced by chemical denaturation is fit by the above equation, that means the equation we just saw. So, it is essentially fit by this equation y of t, where the respective parameters or the respective stuff we have put in, or the items have these expressions, right. Okay, moving on, the equation has 6 adjustable parameters that are needed to fit a single unfolding transition. You will see there are 4 which come from what, m, there is alpha, beta, and then there are 2 in the equation itself. What are the other 2? You can see here, one is the delta G H2O and the other one is m. Essentially that is what you are doing, everything else is a constant for you, T is a constant, R is a constant. Okay. So, there are 6 adjustable parameters you can do, and again you do a nonlinear fit to your observed transition. Now, m has the dimensions of calories per mole per molar concentration of a denaturant, and that is very straightforward to look at. So, what was what was your delta G? Your delta G observed was equal to delta G H2O, right, minus m, I can write what, concentration, right. So, if I take the value of m, the unit of m, what will it be? It will be essentially delta G minus delta G H2O over concentration of C or over C. Delta G minus delta G H2O, I told you we are always talking about molar free energy change. So, it is calories per mole or some energy unit per mole, and then you also have C. So, it is change in free energy per mole per molar concentration of denaturant. Is it clear? It is very important. Okay. So, let us take an example of chemical denaturation. So, this is typically a certain observable y, let us see what I have here. Okay. I can just write y out here. This is a certain observable y, and I am observing the change in y as a function of denaturant concentration. So, on x axis you have the concentration of urea, which is a denaturant, right. So, you can understand, if I do this from before, this would be what? This would be y of n, right, because this is where I am starting from. See, this is y of n because why? At 0 concentration this is the highest, this is your folded state, and then not drawn to scale though, but let us see if I can manage, and this is y of d. Okay. Now, as the statement adjacent to the figure says, and to repeat, to study equilibrium between d and n, both must be present at measurable concentrations. If both must be present at measurable concentrations, what transition I am looking at, or what phase of this transition curve am I looking at, or what region I am looking at? Somewhere close to this. So, this is my transition region, and this is the region which is going to give me the most reliable values of delta G, right. So, this is what I am going to use for delta G calculation. This region. So, you can see one thing, only within a very narrow region of the concentration of denaturant do you have the delta G values, whether you are here on the top, that means below that denaturant concentration range, or above that, your delta G does not have much of a meaning, because the respective concentrations or the respective species are not present in measurable amounts, as simple as that. Is that clear? So, now, if you would ever look this paper up by Pace and Shaw, Proteins 2000, I have given it, essentially I have taken the paper from there. Okay. Now, what is this plot? This plot is a plot of delta G versus urea concentration, and it is not surprising that it is a linear dependence on urea concentration, because that is what we started with, right. We said that delta G was equal to what? Delta G H2O minus m concentration of denaturant, and that is what you are seeing. It is a negative slope. So, the thing is like this. Now, let us see. Now, what is this value? Can someone tell me this value? Very good. So, this is delta G H2O, right. Now, you look at from this portion, say from this portion to this portion. If you do this, are there any points, any measurement points? There are no points from experiment. There are absolutely no points for experiment. See that, and you can see where are we when we do not have any points. These region corresponds to which concentration? Say 1, 2, 3, 4, even 5 molar urea. See, we are not being able to calculate delta G, especially for this protein. Why? Because under these conditions your protein is not necessarily showing much of a change in its signal. Why? Because you do not have enough of the denatured state present. So, the only region you are really focusing on, is this one. This is what you are focusing on, and the rest you are just, what are you doing? You are just extrapolating. So, now you understand what this linear extrapolation is all about. So, you get delta G over a very small range of denaturant concentrations, and then you, assuming that linear dependence, you extrapolate it to your y intercept, and you get the value of delta G H2O, which otherwise would have been very difficult for you to get. So, is the hypothesis clear? Is this linear extrapolation method clear? No, this is routinely done. This is routinely done. Okay. Okay. Now, let me go forward, then I will again come back to this. So, what does this say? The first statement says that unfolding can only be studied at approximately close to 7 molar urea. Now, why is 7 molar urea so important? You go back, see what happens at 7 molar urea. You are very close to that line where delta G is equal to 0, and what happens at delta G is equal to 0? In this case, it is not Tm, it is called Cm, because temperature is not changing, right. So, but delta G is equal to 0 means you have equal concentrations of native and denatured, and that is why 7 molar is very close to that point. So, you have appreciable amounts of both. Okay. Next, long extrapolation is necessary to estimate delta G H2, and that we just saw, because over that region we do not have any points at all, we just cannot have any points. At the transition point, delta G is equal to 0, right, that because you have equal amounts of denatured and native state. Also, delta G is equal to delta G H2O minus m concentration of denaturant. This is the hypothesis we have started with. So, what will happen at the transition midpoint? So, at the transition midpoint, this delta G would be equal to 0. Okay. So, I can write at the transition midpoint delta G is equal to 0 as I have written here, and hence delta G H2O is equal to m concentration of denaturant, but it comes with the tag a subscript which is 50%. What does it mean? 50% means I am just at the midpoint, it is called the transition midpoint, exactly like your T of m. So, like T of m, you have a very similar thing out here, it is C of m, right, and that is what delta G H2O is equal to m C of m is talking about. So, C of m is essentially that concentration of a denaturation species which brings about 50% change. That means you have 50% unfolded, 50% folded. Okay. that is what it says, where Cm is the denaturation concentration or the denaturant concentration at the transition midpoint. Okay. So, I can further write then that because we have just proved that delta G H 2 is equal to m times C of m, then I can rewrite this equation as replacing delta H2O by MCM, and hence this is what I have. Okay. So, I will just go back and I will mark the corresponding thing. So, this is your C of m, is not it? This is where C of m is, okay, because it corresponds to the delta G is equal to 0 line. See, everything is, you do not have to remember anything, right? You just look at the figure and everything is so evident to you, because you know what you are plotting. You are plotting delta G versus urea, and then everything follows, right. Okay. See, all this time we have been talking about urea, we have not mentioned guanidine hydrochloride that much, right. Now, think about this. Suppose I have an experiment where I do the denaturation with urea, right. Now, I take another experiment where I do the denaturation with guanidine hydrochloride. See, both are going to maintain the same linear variation. Now, your denaturation midpoint might be different, because the strengths of these denaturants are not the same, but the linear variation would be maintained. Now, what you would expect then is delta G H2O should be the same. Because what was delta G H2O? Delta G H2O was that free energy of unfolding where there was no denaturant. So, it does not matter whether I use urea or guanidine hydrochloride, if I extrapolate these things back to y axis, I should be getting back the same value. That is what you would expect based on this linear extrapolation method. But do you see the same thing happening here? No, right. So, here again we are plotting this delta G. So, u is essentially unfolding, right, like your d of n. M is the slope of delta G versus denaturant, and for urea, if you look at this y is equal to, you can see this intercept minus mx, here x is your concentration of urea and y is essentially delta G. So, you can see this is urea, right, and then in bottom you have denaturant, I mean sorry, guanidine hydrochloride. Which one has a bigger slope? Guanidine hydrochloride. If it has a bigger slope, that means your delta G has a steeper dependence on guanidine hydrochloride than urea. And what does it mean? It means, or it boils down to the fact that the guanidine hydrochloride has more strength as a chemical denaturant than urea. That is simply what it is saying, right, because there is a bigger change in slope, right. Okay, let us not bother about that. So, this is the main thing. Both guanidine, which is guanidine hydrochloride, and urea should extrapolate to same value of delta G H2O, right, delta G unfolding, remember H2O, which is about 4 kilocalories per mole approximately, but you do not have that. There must be a reason behind this, right. So, people have been really bothered about this. So, people have tried to explain this. How can you try to explain this? So, what people have done is, this linear extrapolation method is one model definitely, but think about this. If guanidine hydrochloride has some electrostatics involved in it because it is a salt, urea is a polar molecule, then there has to be some specificity or some changes in the types of interactions when you have guanidine hydrochloride interacting with the protein as compared to urea interacting with the protein. The simple reason being, proteins have charged moieties too, especially on the surface. So, if you would be having a charge interacting with a charge as opposed to a polar molecule interacting with a charge, obviously the effect would be different. Is this difference arising from there? So, what people did is they tried another model which is called a transfer model. What is this transfer model? So, you look at this thermodynamic cycle, you can have the native state in water, you can transfer the native state in water to the same N in a certain concentration of urea. Now, also this native state in water can go to D in water only. If N in water is going to D in water, then that free energy change is what? Delta G H2O, because it is only in water. That is the intercept you are getting, remember. Then N in water goes to N in urea, that is delta G transfer of the native state. That is why it is called delta G transfer in brackets N. Then you go to the right hand side of this cycle, D in water goes to D in urea. So, this one is delta G transfer of the denatured state, and finally what you have is N in urea will go to D in urea, and that is what you essentially follow, that is what your delta G is. So, this is what the thermodynamic cycle is. The only new thing that you are putting in now is your delta G transfer, and this transfer, remember, is very similar to some type of transfer you talked about before. What transfer did we talk about? Neopentane in water, that was the hydrophobicity, right? We talked about it. It is essentially the same transfer you are trying to do, but for a different reason, okay, with a different system. So, what I can write from the thermodynamic cycle is the total change in free energy delta G plus delta G transfer of the native form is equal to delta G H2O plus delta G transfer of the denatured form from this thermodynamic cycle, right. Now, see how this simplifies. Now, what I can write is delta G minus delta G H2O is equal to delta G transfer of the denatured state minus delta G transfer of the native state, just based on the previous equation, and this is equal to you look at, I am talking about this one now, it is a summation of N I alpha I delta G transfer I. I will tell you what these are, but before I go to the next slide, look at this. What is this one? What is delta G minus delta G H2O? Isn't it minus M times C, the concentration of the denaturant, right, times the M. So, you already have a relation between the concentration of denaturant and this whatever you have under summation. I have not told you what you have under summation right now. So, let us look at what this means. We are talking about this whole thing under summation. What is Ni? Ni is the total number of groups of type I in the protein of any type. So, any species I say in a protein, and you know our protein will be having different groups. Then what is alpha I? Alpha is a fraction of groups of type I should be writing type I of type I exposed in D, but not in N. Okay, that means in native state they were not exposed, but when you went to the denatured state, obviously they got unfolded and they got exposed to the surroundings, which is in your case denaturant in water. What is delta G? Now, this is the key term. This is the Gibbs energy of transfer of group I from water to a given denaturant concentration. The same thing we did for neopentane. We looked at the Gibbs energy of transfer of neopentane from its neat phase to what? Water phase. In this case, what are you doing? You are doing this Gibbs energy of transfer from now water to denaturant. That is what you are doing. So, that is what your Gibbs energy of transfer is. Okay. Now, you can do a simplification, well, let us not go into that, but what it just says is delta G is equal to delta G H2O plus delta alpha Ni delta G Tri. So, delta alpha means whatever change in exposure you have, you are saying that it is not that much dependent upon the denaturant, okay, that delta alpha essentially can be brought out of the summation, that means it is essentially a constant. Ni, well, is the number of groups summation, okay, that is fine, but the key issue is your free energy of transfer. So, if you would somehow manage to relate this free energy of transfer to the concentration of the denaturant, then possibly you can relate it to the linear extrapolation method. How? If this is what I am writing, I also know this delta G is equal to delta G H2O minus M concentration of denaturant. So, if you compare these two, equations, what does your delta G transfer I roughly correspond to? It corresponds to minus M times the concentration of denaturant, isn't it? The other ones I am saying are essentially constant. It is essentially a transfer free energy which now is going to depend upon your denaturant concentration with a certain slope which is minus M. Okay. And if you are going to do that, and you know this has been done by people experiment wise, if you are going to do that, now this is a curve you get. So, these are for different amino acids, but do not worry about this. What you essentially should worry about is on this side, the right hand side you have urea, which is written at the bottom, and on this side you have the guanidine hydrochloride. GDMCl is often the short form used for guanidine hydrochloride. Okay. Now, from the previous slide what I had said was delta G transfer should correspond to what? Minus m, I can write C. Now, what does this immediately tell you? What it immediately tells you is, 1, obviously it varies linearly, but 2 is when concentration of, when C is equal to 0, that means concentration denaturant is equal to 0, what will happen to delta G of transfer? That will also go to 0. So, if you, now this is what you have derived. Now, this should be independent of what denaturant concentration, of what denaturant you are using. It is absolutely a universal truth. So, if this is maintained by whatever denaturant you are using, then you know that typically they are acting in a similar fashion by the same mechanism, no difference. But look at what happens in urea. In case of urea, see you are starting from here 10 molar and you go back. In case of urea, which is the right hand side, each and every curve goes to 0 at 0 concentration of urea, is not it? All of them extrapolate to 0 at 0 concentration of urea. But is it the same for guanidine hydrochloride? It is not the same for guanidine hydrochloride, right? What is it? You always get something which is below that, right? What does it mean? You are actually overestimating it by a certain amount. Remember, you are always below 0, right? Okay. So, let me just go forward. The same thing which we just discussed is going to come up on the slide now. If you are going to apply linear extrapolation method to this transfer model, then the transfer free energy must vary linearly as a function of the denaturant. That we have seen already, it is applicable for both. Now, the delta G transfer must go to 0 at 0 concentration of denaturant, okay, but this does not happen for guanidine hydrochloride. So, then what we can say is the linear extrapolation method holds for urea, but not for guanidine hydrochloride. This is a proof of that. And next, therefore, delta G H2O calculation will be overestimated for guanidine hydrochloride induced denaturation. It will be overestimated, remember, because delta G transfer should have gone to 0, but is actually not going to 0. It is giving you a finite value, and that is why your delta G H2O is being overestimated. Do you understand why delta G H2O is being overestimated? Just go back, look at the equation, compare this, and you will find out why. Okay. But having said this, just look back what we had. Now, see, do not you find the same thing happening here? These are two curves, the blue one is guanidine hydrochloride, the black one is urea. Do not you think that the guanidine hydrochloride now is being overestimated? It is because of exactly the same reason you just saw that delta G transfer was not 0 for guanidine hydrochloride. So, the bottom line is this, the bottom line is that in guanidine hydrochloride, the mere fact that it is a salt will give rise to something which salts do. What is that? Ionic strength. That ionic strength would have a huge role to play in the mechanism or the way this guanidine hydrochloride interacts with the proteins, because it will start disrupting or interacting with the charges much more vigorously as compared to a polar molecule like urea. And that is the reason, that is precisely the reason is essentially then electrostatic in origin, right. This electrostatic in origin, this reason is precisely why guanidine hydrochloride does not follow the LEM method rigorously, because it is not a polar molecule, it is a charged species, and this charge brings about a change in the way it interacts with the corresponding protein molecule when you compare the same with that of the interaction of urea, right. So, keep this in mind. Linear extrapolation method is very much applicable for urea, but is not so reliable when you talk about guanidine hydrochloride. And how did we know that? Because if you are going to extrapolate to get delta G H2O, you better have the same delta G H2O for both, because delta G H2O is a thermodynamic parameter, 0 denaturation, it does not change, it has to be the same in both the cases, but it was not. So, this was one of the eye openers, like there is a very good there are quite a few very good papers on this denaturation, chemical denaturation. It's I mean, let me tell you this, the mechanism of denaturation is still being sought after and is still a very hot topic of research. But even when people were talking about the thermodynamics, then people realized this fact that guanidine hydrochloride was not satisfying your LEM criteria, and people have from then on been trying to explain why, and this is the closest answer they have got. Obviously, it depends upon the specific protein. For example, if you take a protein which does not have very well defined charge residues, then they will be very close to each other. If you have too many salt bridges on the protein or other specific stuff, then you would expect the difference to be larger and larger. Okay. So, what do we have next? Let us see. So, we talked about this, we talked about the applicability, right. Now, M values, the dependence of M values on accessible surface area. Remember this accessible surface area we talked about, when did we talk about? When did we talked about when we were talking about this hydrophobic effect, right. And we said that change in delta Cp, whatever change in delta Cp or whatever change in Cp you are having, the delta Cp was essentially because of this ordering disordering of water molecules. And remember, the more hydrophobic stuff you expose, there is a more accessible surface area you expose. That means that surface is being accessed by your denatured molecules, and hence the more of delta Cp effect that is coming in. That means delta Cp is also inherently related with your accessible surface area. Okay. Because the more hydrophobic residues you expose, the more of water ordering you have, and thus those are the water orders you have to break, just increasing the delta Cp. So, look at this plot. So, this is a plot of your accessible surface area against the number of residues in a given protein. And see, it is very obvious, right. The obvious thing is, if you would increase the number of residues of a protein, your accessible surface area would also increase, and you can see almost a very good linear correlation with a pretty high R value, okay, with a pretty high R value. So, then coming back to the question that you asked yesterday, if you would know the number of residues, right, and you can see you have this linear relation, then at least you can estimate based on the number of residues what your accessible surface area would be, the total. And then this accessible surface area is composed of two things. One is accessible surface area coming from your non-polar groups and accessible surface area coming from your polar groups. And the paper I will refer to has actually an in-depth analysis of both, but will not go into that. It is just that you have the idea that M value will depend upon accessible surface area. Why? Because accessible surface area depends upon the number of residues. I will soon see that. So, amount of accessible surface area correlates very strongly with the number of residues. Okay, that is what is proven here. So, what they did was, so this is the reference I have taken the figure from. It is a very good paper. I think it's all of you should read it. Now, you are doing, or you are plotting M against accessible surface area. What was M? Remember that the slope, and in this case it is for urea. So, what do you see? There is some scatter, but essentially you also have a kind of not very strong as the one you saw before, but you have some well defined linear relation. Okay. Only in this case your nature of fit is poor because your R value, you see, it's not close to 1, it is what, 0.8. So, it is far off from that, and you do have a lot of scatter. Now, why do you have these scatters? One is proteins with disulfide links or disulfide cross links, I mean, they are the open circles. So, these are the open circles. So, these are the open circles. So, these are the ones with disulfide links. Now, is not it obvious, if you have a protein which has no disulfide bond, if you have a protein which has a disulfide bond, which one would be exposed more? The no disulfide bond, very simple. That means, the amount of surface or amount of accessible surface area for the one which has no disulfide bond would be more than the one which has disulfide bonds, because the disulfide bond would do what? They would bring them together, resist denaturation, because it is a covalent binding, right. SS is a covalent binding. Okay. Hence, you can see that this all these circles, they essentially lie below that straight line, the fit. That means, the M value is smaller than what you expect for a protein having similar number of residues, but no disulfide bond, because it is not getting exposed that much if you have a disulfide bond. So, the same paper, if you would go through the paper, we are not going to that thing here, but if you would correct your model by putting in a certain correction for disulfide, then you will see that the relation R would tend to 1. That means, it would become much better, because then you are taking your disulfide cross linking into consideration. But anyway, the bottom line is that M does depend upon the accessible surface area, and so does delta Cp, is not it. So, that M and delta Cp are very closely related. Okay. Now, let us look at this very interesting aspect, effect of heat capacity and M value. What are you doing here is, here you are plotting delta G versus T for two hypothetical proteins, right. It is a model, this is just a model, people have modeled these delta G curves. So, here it is a thermal case where you are plotting delta G as a function of temperature. You have two proteins A and B. Okay. So, these are the two proteins A and B. So, I think this one is the corresponding delta G curve for B, and this one is the corresponding delta G curve for protein A. And remember, this was your stability curve which we talked about before, right. So, how did they actually simulate this? They said that for protein A, delta H is about 70 kilocalories per mole and delta Cp is 1 kilocalorie per mole. For protein B, delta H is 120 kilocalories per mole and delta Cp is 2.5 kilocalories per mole, right. Now, the mere fact that delta Cp in both the cases are different, what is the immediate effect you see on the curves? If I had not given you this delta Cp value, would you have been able to predict which one has more delta Cp? How? Del okay, or there is a more direct relation, we talked about something.
Cp square del H by del T. So, when the range is high, curve is like this. So, del H by del T, the change in unit temperature that brings the change in del H will be large.
Hit the point. What are you talking about? You are talking about a curvature. You should not be forgetting that. What is the curvature? It is del 2 del G over del T squared. What was it equal to? Remember, it has a relation with delta Cp. That is what you are looking at. If your delta Cp is high, that means the curvature would be very high. If your delta Cp is low, that means the curvature would not be high, it would be shallow. That is what you are looking at, right. So, if you are given a plot like this, you should be able to figure out which one has more delta Cp value just based on the curvature, and B has more curvature than A, is not it, and that is what it figures, because for B the delta Cp is 2.5, for A the delta Cp is 1. You have to be able to hit the point just like that, Okay, you know these thermodynamic relations. Okay, that was one. Now, what is the consequence? The consequence is, you look at this, where, see which one has a higher Tg or Tm value now among A and B? I am not talking about the cold denaturation, I am talking about the heat induced denaturation. Which one has a higher Tm value, heat induced? How can it be B? Where, what is your delta G definition of Tm or Tg? It is a 0 line. Which one crosses it at a higher temperature? A crosses it, right? So this is A. This is so this is the Tm for A, isn't it? And this is what? This is the Tm for B. Okay. You are happy with this? You are happy with this? Okay, I am also happy that you are happy. But then the problem is this. Well, Tm and Tg are the same. There is no problem with that. But the problem is this, you look at this. Remember, this delta G we are talking about, the delta G which is plotted is your delta G unfolding, right? And it goes to a maximum. Remember that point of where delta G is maximum? Where is the, which one has a more delta G maximum? Which one has a more delta G? A or B? B. Right. So this is, see if I do this, this is delta G for B, and I don't have, I am just slightly displacing it, and this is delta G for A, and delta G for B is more than delta G for A. But this is weird, isn't it? It is not weird. Okay, good to know, but let me tell you where the weird part is, because I feel it is weird, right?
Actually, that delta G is not.
Hold on. Huh? I know you are excited, so just hold on. The fact that Tm of A is greater than Tm of B, what does it mean to you?
Delta G 0.
Delta G 0 occurs at a higher temperature for A than for B. Does this have any other meaning to you? Yeah. So what he is saying is right. You think about this. What was K equilibrium? K equilibrium was concentration of D by concentration of N equal to 1 at Tg or Tm. That means the fact that I have 50% of both at a higher temperature means that to get to that 50% of both, I would be needing a higher temperature. So essentially, I would be needing more thermal energy to denature A. But you come down to the room temperature, the normal temperature, the ambient temperature. What do you see? Which one has more conformational stability? B has. Okay. So just let me move on. So these are written in the slide. So one thing is the higher value of the higher value of actually this one should be writing delta Cp. The more curved is delta G as seen from the figure. Okay. Now let me give you the data. Protein A has a Tm of 90 degrees, protein B has a Tm of 70 degrees Celsius. Okay. Delta G at 25 degrees Celsius, which is the ambient temperature for A, is 6.3 kilocalories per mole. For B, it is 8 kilocalories per mole. This is what we just discussed. Thus, at normal temperature, B has a higher conformational stability than A at normal temperature. Remember, can this be explained based on the data provided? We were just trying to do that. Small proteins can have high Tm values, though the conformational stability might not be high. Okay. So again, think about this. The mere fact that Tm is higher for protein A as compared to protein B does not guarantee the fact that protein A is more stable than protein B. That is the point I was trying to make. Okay. Protein A can be a small protein which is what it is saying out here, and its conformational stability might not be that high at room temperature. Protein base A is a huge protein, it has so many interactions, its conformational stability might be pretty high at room temperature, but when you denature it, protein B possibly would denature earlier than protein A. Now, why I am raising this point? I am raising this point because just looking at a Tm, it is then very risky for you to make the statement that because its Tm is higher, my protein, that protein would be stable than the would be more stable than the other protein where the Tm is lower. Sure, the protein which is a higher Tm is possibly more stable at that temperature where protein, the other protein denatures, but it is not more stable at the temperature where you are actually looking at it, that is the normal ambient temperature. So, please again pay attention to this and keep this in mind. This is not something you come across regularly, but see, thermodynamics cannot be defined. You have done just a modeling, that is why I said there are two hypothetical proteins, right, there are two hypothetical proteins, and based on thermodynamic modeling, the way you have tried to model it, this picture actually emerges. So, you have to redefine what Tm is in terms of protein stability. So, essentially now what Pancham was saying is look at the last statement. One should not judge conformational stability of a protein from a very high value of Tm. Okay? If this thermodynamics of that pair of proteins gives you this information from your thermal, it should give you the same information for your chemical denaturation, because both of these follow the same thermodynamics. Now, see what they have. You look at A, well, it is not visible, you look at A and look at B, right. So, you can understand this is B and this is A. How can I do that? Even without trying to look at the legend, I will be able to do that. Why? Because look at M, which is a higher value of M, A or B? B as. So, B will be changing in a steeper fashion than A, is not it? So, we immediately know which one is B, which one is A, good. Now, look at the midpoint of Cm, what happens? I mean the midpoint of denaturation, the Cm for A is 6.3, but for B is 4. You are essentially seeing the same thing as you saw for thermal denaturation, is not it? So, again, but B has more conformational stability, B has more conformational stability. How do you know that? You look at delta G at 0 denaturant, you look at delta G at 0 denaturant, which one has more stability? B has. Okay. So, again one should not be judging conformational stability from either a higher Tm or a higher Cm, and let me see whether I have the other statement here. So, I do not have it here. So, what it means is your Tm or Cm essentially just gives you this information. What information does it give you? It gives you this information that it is that temperature where I have 50% denaturation. It is just that temperature where I have 50% denaturation. But in most cases, for people who would do or who are doing research with proteins or working with proteins, you would see that in most cases Tm would actually conform to change to protein stability. But the idea out here is it is not always the case. So, you do not always correlate Tm and Cm with stability of a protein, but remember this is a stringent case, this is a hypothetical case, you have just explained it based on your thermodynamics, okay, nothing else, because protein unfolding folding is what we are concerned about, mainly the thermodynamic parameters, and that is what we have taken care of. There is no other assumption involved. We have already seen this, and that is what we have used to do a hypothetical model. Okay. So, I will well, we will stop here. That is essentially bringing us to the end of chemical denaturation. Next class, what we will do is we will try to look at some mechanisms what people think that chemical denaturation, the mechanisms they invoke to denature proteins, and then move on to other types of denaturations. Okay.